AP Physics, 2014, number 2. It's this one. I'm going to do it on a separate sheet of paper. This is my original here. So we have a little block up here, and it's going to slide down here, frictionless. It's going to slide around here, and this surface is frictionless, but the little wall of this little circle is not frictionless. So this is the little top view of that. Okay, so in the first part of 2014, number 2, first part of that, I'd like us to derive an expression for the height of the ramp h. And we know that when it gets to point P, it's got a velocity of v sub 0. So we've got something that's changing height, no energy loss. So that means the gravitational potential energy it starts with is going to be kinetic energy when it gets to point P. So the mass of it is m, g. They actually just call that height h. Sometimes it's a y or an L or something, but here it's just h. And that would be equal to 1/2 m times its velocity squared. So h is equal to v sub 0 squared over 2g. Right? Our m's cancel out. All right, there's part A. And then part B, a short time after passing point P, the block is in contact with the wall and moves with the speed of v. So we got friction from the wall now, slowing it down. Excuse me. Is the vertical component of the net force on the block upward or downward. So what they mean by the vertical component, I thought that with the way they describe these components is a little bit confusing. Vertical, they mean the part that's like coming straight up out of this plane. And the net force is going to be 0 there because there's different ways you could say this. You could say that gravitational force is equal to the normal force. You could say that there's no motion in the vertical direction. Something like that. Ain't nothing happening in that direction. Part 2, ditto on the possible confusion here. So they want you to draw, if here's the rough strip here, and then the circle starts and comes around like this, and when it's right here, when the block is right there, they want us to draw in the net force. So they mean here the net force, the horizontal component is the part that's in the same plane as the table. So we're looking down on the force that would be like in this plane right here. So, well, there would be a normal force from the wall here toward the center. That's the thing that's allowing it to move in a circle. But there's also friction that would be opposing the direction of motion. So I have some this way and some this way. So it would have to be, the net force would have to be somewhere into that, like quadrant 3 if you were looking at it, like they were quadrants. And different ways you could justify that. So the vector sum would be the normal force plus the force of friction. And the normal force is down, normal force is that away, and the friction force is that away. So you can justify it something like that. And let's see, now express your answers to the following terms of v sub 0, v, m, r, mu, and fundamental constants as appropriate. So they want us to determine an expression for the magnitude of the normal force exerted on the block by the circular wall as a function of v. Well, I don't know. I guess it's possible to get confused and freaked out by that. But the thing I think that we have to worry about, or think about, focus on rather, is that this is circular motion. And in circular motion, excuse me, the sum of all forces is equal to mv squared over r. And the r here is capital R, so I'm going to use that. And the sum of the forces toward the center of the circle, this is the sum of the forces in that central direction. The sum of the forces in that central direction, it's just the normal force. That's the only thing. So the normal force is equal to mv squared over r. And that's all they're looking for in this part. That is an expression for the normal force as a function of v. So as it slows down, there's going to be as it slows down, as v gets smaller, there will be less normal force. In part D, derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed of v. So the tangential acceleration, that's happening because of the friction, right? So the tangential force, in other words, the force that's perpendicular, that's opposing the direction of motion here, tangent to its circular path, is just the friction force. So the tangential acceleration is equal to the friction force, which is mu times the normal force. Any kind of force, we can make that substitution, right? Let's see, let's just fill out what we have here. So normal force is mv squared. Again, they're kind of holding our hand here as we go through this. They got this for us first, so probably be expecting to use that. And then the m's cancel out. So the tangential acceleration is equal to mu times v squared over r. I'm going to put the mu and the r here because those are the constants. That's all. And in part E, this is a rare example. In fact, it's the only one that I can think of where you need to do a differential equation, but they don't say that. Usually they set you up there. But here they want us to derive an expression for v of t, the speed of the block, as a function of time after passing point P on the track. Well, this is the key right here. And the key is to recognize that since I have acceleration as a function of v here, I could replace that with velocity and then do some calculus. So this is a separation of variables problem. So v to the minus 2, if I bring it over here, dv is equal to mu over r dt. Anti-differentiate, that's minus v to the minus 1 is equal to mu over r t plus c. And the initial condition, I know, I don't think there's ever going to be a situation in physics where we're left with this plus c. I think we're always going to be able to solve for that with some initial condition. Here, it's that at time 0, the initial velocity is, the velocity is v sub 0. So at time 0, the velocity is v sub 0. So that means when I plug 0 in for t, that would make that go away. The c is whatever has to be to make this true, so that means the c must just be also negative 1 over v. So moving up to here, I've got that. I think that's right. Like I might be missing a negative now. I don't think so. I believe that is good. And then, excuse me, multiplying through by negative 1, that would flip this, and it would give me v Just change the order of those. Flipping over both sides. Don't do any bad algebra now and flip those individually. You can't do that because it violates the rules of the universe and spits in the face of everything that is true and beautiful. So I think it's this. That is what I got. It's my answer. I'm sticking to it. Oh, can you see that? There it is.